All right, so now we're going to talk about trigonometric substitution. And as you can see, you have a table that has all the possible trigonometric substitutions. Now, the problem that I found with this, all right, is that when I looked at them, they just didn't make a whole lot of sense for me. Now, in terms of what we're talking about here are the identity functions, which is nothing different. That's what you learn in pre-cal. But how this relates to this is what I hope to explain to you in a way that you perhaps do not have to memorize this, okay? Or try to even just recognize those type of patterns. So when you have a function like this, when you're integrating a function like this, we're gonna try to relate to this to a right degree triangle. Okay, so here's what I'm trying to say. All right, this top part, if you look at it, the top part is the square root of 9 minus x squared. Now, that looks suspiciously like the formula for Pythagorean theorem. All right, so x squared plus y squared, I'm going to call this 3 squared, and you'll see why here in a second. All right, so essentially I took that 9 and I took the square root of that. So again, you may not see where I'm going, but hopefully it'll all make sense here in a minute. Okay, so now that I have this, all right, I'm going to write this as x squared plus y squared is equal to 9. And I'm going to solve for y. So therefore, I'm going to take the square root of each side. So y is equal to 9 minus x squared, square root of that. All right, so let's call this side, since we know this is some kind of Pythagorean theorem. And if you look at it, right, the way that I have written this should be 3. I'm going to call this x, although to you that might not make sense because we normally call that y. But I'm going to tell you right now that whether I use x there or y there is completely irrelevant to what I'm trying to do. And this side right here would normally be y, but now I'm going to call that the square root. Instead of writing y here, I'm going to write the square root of 9 minus x squared. So you might be thinking, well, that's pretty neat, but how does that help me? So this is how this is going to help you, right? I'm going to try to substitute all of this, and I'm going to show you how what I'm about to write is exactly what's on that table. So first, I know if I make this angle theta, I know that the sine of theta is equal to the opposite over the hypotenuse, right? In this case, that's x over 3. So I can say that x, if I multiply both sides times 3, I can say that x is equal to 3 sine theta. Okay? At the same time, what I'm trying to do now is now I can replace the x's, all right? Now, I can go ahead and plug all that in, but if you look at it, I do have the square root of 9 minus x squared just hanging around there, and I can find a way for me to substitute the whole thing with one trigonometric function. So what I'm going to do now is now I'm going to use the cosine. The cosine of theta is equal to the adjacent over the hypotenuse. So I can say that the square root, if I multiply both sides times 3, the square root of 9 minus x squared is equal to 3 cosine theta. All right? And the last but not least, what I'm going to have to do here is I'm going to have to take that x that I found here, all right, which is now this, and I'm going to take the derivative of that. So again, if I say that x is 3 sine theta, then dx is going to be 3 cosine theta d theta. So I'm going to use all of this, all right? So I'll try to use some different colors to help you out to substitute everything that I have here. I'm going to substitute this right here with cosine. I'm going to substitute x squared with this right here. But of course, I'm going to square this sine also, right? So I'm going to square the 3 sine theta to make that work. And then I'm going to replace this. I'm going to replace this dx. I'm I'm going to replace this dx with what I just circled there. All right, so I'm going to just substitute all of that into that equation. So what I end up with instead is I'm going to end up with 3 cosine theta. Right, I just replaced the square root of 9 minus x squared. And now x squared is going to be 9 sine squared. Right, I guess I can write it like this if you want me to. I don't want to skip too many steps. I may lose Brock in the middle of it. It's probably too late by now, but that's okay. So now we're going to substitute that dx with 3 cosine theta d theta. Okay. So now all we're going to do from now on is just basically combine or multiply the two cosines. Just basically multiply everything out. Those are the 9s that are going to cancel. Cosine squared over sine squared is cotangent squared. Now, once you get to this, all right, then you are basically free to try another method. Now, it will require some work. So, for example, I don't know what the cotangent square of theta is, but what I do know is I can use a trig identity, right? Specifically, a Pythagorean trig identity, and I can say the cotangent square of theta is cosecant squared theta minus 1 d theta. All right, so now the antiderivative of cosecant squared is negative cotangent. The antiderivative of negative 1 in this case is just going to be negative theta plus c. All right, so finally what I have to do is I have to use the same triangle, this triangle right there. All right, we have to use that same triangle to substitute for the cotangent of theta and also theta. All right, so let me use a different color here. Let me use purple for fun. All right, so I will now, let's see, cotangent, right? So cotangent of theta would be the opposite of tangent. So tangent is normally opposite over adjacent. So I'm going to do adjacent over opposite. So cotangent of theta is going to be the square root. Again, I'm using this triangle. That's what I'm getting that from. Of 9x squared over x. Okay. So I can get rid of that cotangent right there and replace it with this. Now I'm going to use this equation right here, the sine of theta. And I will take the inverse tangent to get rid of the sine because I want to end up with theta only. So I'm going to use the inverse sine on both equations. And when I do, I end up with this. And then finally, all I'm going to do is substitute that back. And that's going to be my answer. Now, the reason I like this, doing it like this instead of trying to memorize those tables, because that's about the only other choice you got, is that I feel this is a little bit more intuitive. And you know that I'm always about not memorizing as many things as I can. Obviously, there's some things that I do have to memorize, but this shouldn't be one of them. All right, so that's the answer for that. All right, so let's take a look at, so again, notice that this worked for a constant minus x squared, the square root of that. Okay, so be aware of that. I guess the only thing I would say with the table is that you got to be able to recognize that you need to use trig substitution, okay? Otherwise, by the way, if you don't want to do it my way, you can just basically look at what they have, say right there, and you can just plug in a sine of, or in this case, 3 sine of theta for every x that you see and try to solve. But I promise you that's actually more difficult. There's a lot more trig involved than that. All right, so let's look at example number 9. All right, so when I look at the square root of two numbers that are squared and whether they're subtracted or added, I always think, well, maybe trigonometric substitution works. All All right, so in this case, this one took me a little while, right? Because on this one, oops, I made that really big. Let me switch that to my black pen here. I have to write this as y squared plus 4 squared is equal to x squared. So, of course, it did take me a little bit. I had to sit there for a little bit and figure out a way that when I subtract, for example, x squared, if I subtract the 4 squared from this side, which would be 16, all right, and I take the square root. So this is the part that took me a while. So this is essentially what I'm going to try to do, okay? So I have x squared minus 16. So once you figure that out, then you can come to this triangle and call this theta. All right, and I know the way that I wrote this, right, the reason I wrote that formula first is because now I know that my hypotenuse is going to be x, and one of these sides is going to be y. In this case, I'm going to name this y, and I'm going to call this 4, okay? Again, you can kind of see how this triangle and this Pythagorean theorem are related. Right, so I honestly think that this is honestly one of the hardest parts to do is just the triangle, all right? So what I'm going to try to do now is I'm going to try to find some equations, whether it's cosine, sine, tangent, or even cotangent, cosecant, whichever one that would make this a lot simpler to do. So here's the deal. At first, I went ahead and said, well, what if I just use cosine, right? And by the way, you may not want to write this down. I figure out pretty quickly here that was not going to be something that I wanted to do. All right, so the cosine of theta would be 4 over x. And if I try to solve for x, I'll multiply both sides by x, divide by cosine, so x is equal to 4 over cosine theta. Excuse me. So it was at that point that I realized, well, it doesn't seem like this problem is going to get any easier if I replace x with 4 over cosine, all right? So I had to think of something else where I don't have some kind of rational function. So I thought, well, what about secant, right? Secant is basically the same thing as cosine, just the other way around. So we have the secant of theta. Remember, secant is 1 over cosine, which means that's going to be hypotenuse over adjacent. All right, and if I solve for x, x is going to be equal to 4 secant theta, right? And I did that by multiplying both sides times 4. So again, I kind of realized that this was not going to work, okay? So don't pay attention to that. Don't get lost in this. So I'm going to try to do the same thing with the square root of x squared minus 16. I'm going to find a way, okay? I'm going to try to find a way to use some trigonometric function that has x squared over 16 in a very simplified way. So here's what I'm saying. If I use tangent of theta is going to be the opposite over adjacent. Now, guess what? If you do that wrong, if you do it the other way, we'll just do it the other way, all right? This will take practice. So therefore, 4 tangent of theta is going to be equal to the square root of x squared minus 16. Okay? So now I have almost everything I need. The only thing I don't have is dx. But I can take the derivative of secant, and the derivative of secant, I believe, is secant tangent, or 4 secant, excuse me. So this is 4 secant theta tangent theta. So now I have everything I need to replace all of this. All right, so I'm going to use substitution now. I'm going to use different colors again. I'm going to substitute the x with this. Okay. Let's see what else. I'm going to substitute the square root of x squared minus 16 with this. And I don't really know what other colors I was using. I'm going to substitute that dx with all of this, okay? So again, I'm just circling everything that I'm doing. So here we go. The square root Now, x squared minus 16 is going to be the 4 tangent of theta. Well, that was done. And I guess if I look at it, I actually didn't even need the x until I just looked at it. I just realized that. Okay, I don't really need that. All right, so now I'm going to replace that dx for 4 secant tangent. D theta. And I kind of forgot to write the d theta over here. Okay. So again, it wasn't until this point that I realized, wait a minute, I don't even need x. All right, so kind of a nice surprise there. So what I'm gonna try to simplify as much as I can. Notice that the 4's will cancel, the tangents will cancel. I end up with the integral of secant theta d theta. And then now, if you look at the beginning of your notes, okay, it tells you that one of the antiderivatives that will save you time if you remember them, at some point we're going to have to memorize those, is the antiderivative of secant, which is the natural log of the absolute value of secant theta plus tangent theta plus c. Right now, what I have to do is I have to use the same triangle to try to figure out what secant of theta and tangent of theta are. So here's why we can do this, okay? How we can do this is, let's see, do I have the secant already? Yeah, it looks like the secant is going to be x over 4 again. So if I take the secant right here, excuse me, I just saw the other one. Secant is right here. I already have that, so that's nice. It looks like the tangent, I already have it here. So there's not a whole lot of work for you to do here. All I have to do is just rewrite that and just replace those two things. So this is x over 4, according to what I wrote here. Tangent is going to be the square root of x squared minus 16 over 4 plus c. And that's it for that. All right, so let's go to the next one. Now, on the next one, again, I have to figure out a Pythagorean theorem here. Right now, notice that I have x squared plus 4. So what that means is that the hypotenuse, more than likely, well, let me just do it and you'll see. So I have x squared plus 2 squared, right, is equal to y squared. And I mean, if you want to call it c squared, I don't care. You can call it whatever you want. I'm going to call it y. All right, so what's going to happen here is I'm going to take the square root of each side, and I end up with x squared plus 4 is equal to y. All right, now if you want me to call that c, I will. I got a feeling that may bother you, but it doesn't matter. Okay, so here's the deal. I know that my hypotenuse is this. That's the one that I don't really have a choice on here. And I'm going to name this 2. I'm going to name that x. Okay? So again, that's what I'm going to do. And I'm going to call that angle theta. And I'm going to go on. Now, on this one, I really do need x. Okay? So I'm going to use the tangent function, the tangent of theta, which is opposite, which is x, over adjacent, which is 2. So x is going to be equal to 2 tangent theta. Okay, so that's that. All right, so I also need to replace the square root of x squared plus 4, so I need to find a way to do that. Right now, obviously, I kind of want to pair up that with a number, not another variable, so I'm going to find a way to include both this number into some trig function. Now, if you look at it, if I have adjacent and hypotenuse, then I have to use cosine, or secant, excuse me, on this one. And hopefully you'll see why I'm using secant. I didn't use cosine because I would end up with a fraction if I do that. The secant is going to be the hypotenuse over the adjacent. And I did that because now when I solve for the square root of x squared plus 4, that's going to give me 2 secant theta is equal to the square root of x squared plus 4. All right. So now I'm going to be able to replace all this. Okay, so now remember that I'm going to replace this x with this. And I'm going to replace, I don't really have a whole lot of things to replace here, but I'm going to replace this right here with secant. And I forgot one little thing, right? I need to take the derivative of this. So the derivative of x is dx. The derivative of tangent is going to be secant squared. Theta d theta. So then finally, I will then replace this dx with this. All right, so let's go ahead and do that. So on the top, all I have is dx, so I will replace that. So I have 2 secant squared theta d theta over, let's see, what do I have in the bottom? I have x squared, so I definitely need 2 tangent theta, and I'm going to square that, but when I square that, I get 4 tangent squared. So I'm going to delete that so I can just write that just to save room. So I don't really have a whole lot of room here. So that's going to be 4 tangent square theta. And then finally, I will replace this right here, the square root of x squared plus 4 with 2 secant. Now this is a part that you might differ. How I do this and how you do this might be different. Okay, but we should get the same answer no matter what. So here's how we're going to do it. This is how I did it. Again, you don't have to do it this way. I went ahead and canceled. All right, I went ahead and canceled the secant. I'm going to switch to black pen here. And I went ahead and reduced this. Okay. Oh, and I just realized I have another 2 here. So this is going to be a 1/2 here times this 2 right here is going to make that a 1/4, which I'm going to put that out here, okay? So now on the top, I end up with secant. And on the bottom, I ended up with tangent squared. Now, on the notes that I had from earlier, I think they used some kind of substitution there. All right, so you could use substitution. I believe they use, actually, I don't know what they use for that substitution. Let me look real quick. I saw what they did. I just didn't like it. I don't know what to tell you. Let's see. They used well, actually, that seems like a whole lot of nonsense to me. But yeah, I'm not really sure what they did. So, but here's what I did. Okay, what I did instead is I went ahead and split that, where I know the secant is 1 over cosine. Oh my gosh.
Pardon this interruption, but if you are in baseball, any of the baseball boys that have stayed behind need to meet in the lecture hall, please. Again, baseball boys, you need to meet in the lecture hall for 8th period today. Thank you.
All right, well, you heard it first. If you happen to be watching this on the same day that I'm making this, well, you better, dang baseball players, better get there. Okay, anywho. So 1 over tangent squared, I can change that to sine square theta over cosine square theta. So all of this d theta, right? So what I did after that, this is secant. So this stuff on the left is secant divided by sine over cosine squared. So again, you may not want to do it this way, but that's the way I did it. All right, so then I rewrote this as 1/4. I'm able to switch this. Cancel that. So now I have basically cosine over sine squared, which I can write that as, I'm just going to write it as cosine x or cosine theta over sine squared theta, which I can then rewrite as 1 over sine, not square, just 1 over sine, times cosine over sine, which then is going to give me okay, 1/4. See, 1 over sine is cosecant, and cosine over sine is cotangent. So I'm going to write it as cotangent cosecant. All right, and the antiderivative of cotangent cosecant is negative cosecant theta plus c. All right, now I'm going to replace that cosecant. Let's see if I have that available. Looks like I don't, so I'm going to have to figure out what cosecant of theta is. Let me use a different color here. Maybe I'll just write for fun. Cosecant theta is the opposite of sine. All right, so I have I'm struggling here, kids. What happened? I'm trying to see what I did. Let's see. Cosecant is opposite over. Okay, never mind. Yeah. So it's going to be x over x squared plus 4. So I'm going to replace this right here with that. Okay, so my answer is going to be negative square roots of x squared plus 4 over 4x, and that's 4x because of this 4 right here, plus c. All right, so that's it for that. So again, guys, this is not easy. Okay, so you're going to have to get better with practice. That's all I have to tell you about that. I don't want to lecture you the whole time. All right, let's go to example 11 and 12. So time for class. All right, so let me do example 11 and 12 here. All right, so in example 11 and 12, we're going to actually use this integrals of inverse trigonometric functions. All right, and the important ones, I think, are these. All right. So basically, if you recognize this integral, all right, then the answer is actually just a matter of plugging it in. All right, so I'm going to have to scroll down, and I'll scroll up here so you can see it. I may even write the equation here. I don't know. So here's the deal, all right? When I see something like this, right, it looks very similar on example 11 to something like, let's see. It looks like this one right here. All right, but except the only difference that you, by the way, use a function and a is a constant. So they just kind of wrote this backwards, right? Which doesn't matter, right? A constant squared plus a function squared is the same thing if you have that backwards, meaning a function squared plus a constant. So same thing. So I'm going to call this, for example, I'm going to write that so you can see what I'm talking about here. So this is a function that they have, and you're going to see how this is basically the same. Okay, so notice that on this one, u is x, and if u is x, then du is dx. All right, so notice that I have that, okay? So that's not a big deal. I have everything I need here. So here's what I'm saying. If I were to rewrite it in a way they had it, okay, this right here, 1 dx would be du, okay? U would be x squared, and a is actually 3, okay? And then we square it, you get 9. So again, this right here is a, the inside of it, and this right here is, excuse me, I did that backwards. This right here is u, and this right here is a, okay? So if you recognize that, then all you have to do is I have to follow exactly this. I already figured out that a was 3 and u was x. All I have to do is literally just replace those three things, all right? So this right here, I'll write the formula all the way for you so you can see what I'm talking about. I don't feel like scrolling back and forth here. So again, I just figure out that a was x and, u was x and a was 3. All right, so the answer, I'm just going to replace that a with a 3. So this is one of the ones that I would love to give you a way to understand this faster, but the amount of time that would take is just not worth it. So this one you are going to have to recognize the pattern, all right? X over 3 plus c. All right, let's take a look at number 12. So same thing, look at the pattern. Can you recognize it? This will look like something you could use. Now, I'm going to tell you right here that the pattern that makes the most sense is this one. There's one that has some minus. There's only one of those, I believe. There's actually two of them, but the other one has a u on the outside, and this one doesn't. This one does not have a function on the outside of the square root. If you get this, the answer is just the arc sine of u over a plus c. All right. So here's the deal. All right. If I make u, and notice that this has to be u squared right here. So if that's u squared, the square root of that should be 2x squared. Are you with me? So therefore, the derivative is going to be 4x, which is really nice because 4x dx is right here. All right, so I will basically replace all of this now. So du now, 4x dx is du. I guess I'll write it right here. I don't know and honestly, this step that I'm writing, I don't think you necessarily would have to write. I'm just showing you how this is truly the same thing. A is 3, u is going to be 2x squared. Okay. And again, 4x dx is du. So this right here is, I'm kind of doing this backwards. This kind of leads into that. Okay, so now the answer, therefore, is going to be the arc sine of u over a, which is 2x squared. U was 2x squared. A was 3 plus c. And that's the answer. All right, so if you recognize the pattern, this one's a lot easier, right? And a lot of this, like u and du and finding out what the constant is, I think a lot of that you can kind of just look at the problem and try to do that in your head, see if it even works. Okay, so let's talk about integration by completing the square. So sometimes we see a level of difficulty with integration that doesn't look like you could do it, but if we do a method called completing the square and then use this inverse of integration of inverse functions or inverse trigonometric functions, that it will actually works out kind of nicely. All right, so this is what we're saying. We're going to use a method complete the square, which we actually did complete the square in algebra. So this is what we do. All right, we're going to rewrite this let me use a black pen. Let me switch back to black here. All right, so we're going to grab this, and we're going to rewrite this. And here's what we're going to do, right? To rewrite it, we're going to grab this 6 right here. This 6 is right here in the middle. We're going to divide it by 2, and then we're going to square it. So that's going to make that a 3 squared, which is a 9. Okay? So what I'm going to do here is I will add a 9 to this. And I'm going to add that 25. But I can't just add a 9, all right? I can't just randomly add a 9 because I want to. I got to be able to get – that function needs to be the same, all right? Or equivalent, I should say. So what I'm going to do here is I'm also going to subtract the 9 like that. All right, so I'm going to add a 9 and subtract the 9. Now, that may not make a whole lot of sense to you, but I'll show you where we're going with this. And where we're going with this is that we're going to factor only this. All right, so we're only going to factor that. So here we go. If we factor this, you would have x plus 3 times x plus 3, or x plus 3 squared. All right, and I'm going to add those two together, and that would give me a 16. All right, and if we go back to those formulas that we're looking at the beginning, all right, so let me go up and look at the only one that has a plus in it, which is the arctangent. Do I have a function squared? Yes. Do I have a number squared? Yes. Okay, so if we call this, let's do this here. If we call u to be the inside of the square function, x plus 3, this is the way to make sure that this actually will work. Du is going to be dx, right? And notice that I have everything I need. So therefore, I can rewrite this as, well, actually, I'm not going to rewrite it. Should I rewrite it? I feel like the substitution is literally identical, but here we go. We have u squared. Now, instead of 16, I'm going to write a squared. So again, I'm going to say that a squared is 16. So a is 4, okay? And then 1 dx is du. And if you look at, basically if you look at this, and then now you can kind of go back and look at your function here, and it's basically identical. All right, so now I'm going to be able to substitute all of that. So the answer for all of these is 1 over a. In this case, a is 4. The arctangent of u, which is x plus 3, over a, which is 4, plus c. Okay? All right, so even if you have a square root like this, you can actually still do complete the square. And I would say maybe complete the square is when you can, like if you don't have any factors, for example, like x squared plus 6x plus 25, there's nothing that factors to it. Okay, so then I think you can then think about completing the square and using the integration of inverse trig functions. All right, so let's do this one more time. Same idea. So I'm not going to worry about the square root for now. I'll show you where that all comes in. But here's what I'm going to do, okay? What I'm going to do, just a second here. Okay, so what I'm going to do here is I will probably pull out a negative, what that looks like a C. I'm going to rewrite this as negative x squared, positive x squared plus 4x minus 21, okay? And I'm going to do complete the square by grabbing that 4, dividing by 2, and squaring it. All right, so in this case, that's going to be 2 squared, which is 4. So I'm going to grab this. I'm going to write an x squared plus 4x. All right, and I'm going to add a 4. Okay, you just have to be a little bit careful with this because you can mess this up, because what I have to do now is I can just, first of all, I'm going to pull that 21 out. This 21 is going to be pulled out, but it's going to be a positive 21. All right, in addition, I can't just add a 4. I got to be able to have an equivalent equation. So what I'm going to do here, I'm actually going to add a 4. And you might be saying, well, I thought that was a positive and positive 4. Wouldn't that make it a positive 8? It doesn't, because this negative right here would make this 4 right here a negative 4, and that would cancel out with that 4, okay? If you don't believe me, go ahead and distribute that negative and add like terms, and you'll see that those 4s will cancel, okay? All right, so now I'm going to complete the square now. So if you factor this, you find out that this is, let me not write this in red. You find out that this would be x plus 2 times x plus 2, which is x plus 2 squared. And then the outside is going to be 4 plus 21, which is 25. Okay, so now I have 25. All right, so what I'm going to do now is I'm going to rewrite this as 25 minus x plus 2 squared dx. All right, so all of that. Gonna lift that out a little bit. Okay, so that's what I got right now. And then now what I'm going to do here is I'm going to call a, which is a constant, or a squared, 25. So a is 5. And u, I'm going to just name that the inside. I mean, I guess I can say u squared if you want me to. And if I take the square root, I get just x plus 2. And if I take the derivative of this, I would have dx. So I'm going to replace all this. I'm going to use substitution, or excuse me, just substitution, I should say, and replace all of this, all right? So this is going to definitely be du on top. And the bottom is just going to be a squared minus u squared. Okay, so that is that. And then when I go back and look at the equations, what does that look like? Which one of these does that look like? All right, it looks like arcsine is the answer for this. And when I say arcsine, remember that what arcsine means, that just means the inverse of the sine function. So the formula says that it's the arcsine of u over a plus c. All right, guys, there was a lot covered here. All right, so make sure you do all the homework. This is really not going to stick unless you do that.